Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 10. Runge-Kutta-Fehlberg Method with Adaptive Step Size Control. The choice of the step size strongly affects the accuracy of any numerical solution. A numerical solution with a large step size tends to deviate from the true solution as x increases, while a step size that is too small leads to an increase in CPU time and also to the accumulation of round-off errors. When the numerical simulation interval from x0 to x0 plus t is very large, it is not uncommon to have a true solution that varies slowly in some subintervals and rapidly in others. Large step sizes can be used where the solution varies slowly, primarily to reduce CPU time without sacrificing accuracy. The step size also determines how often the solution has to be estimated. Hence, controlling it adaptively can provide significant benefits. A variable step size may be used, but applying a variable step size brings about fluctuations in the magnitude of truncation and global errors, as they are proportional to the step size. To obtain a solution with the desired level of accuracy, the truncation error needs to be also estimated at each step to ensure that the numerical solution meets a predetermined accuracy criterion and to adjust the step size if necessary. If the truncation error is extremely small, the step size may be increased. Conversely, if the truncation error is large, the step size is reduced to prevent the errors from accumulating. High-order Runge-Kutta methods are, in this regard, popular and quite reliable schemes due to their accuracy and wider stability range. An adaptive numerical scheme presented here is based on the Runge-Kutta-Fehlberg method, which provides an efficient procedure for solving initial value problems. The method uses fourth and fifth order Runge-Kutta schemes, which use the following coefficients. Next, a current step estimate is computed using the following fourth order Runge-Kutta scheme. An improved estimate is obtained with the fifth order Runge-Kutta scheme as follows. An error estimate by the difference between the two solutions is proposed as the user only specifies the step size h and a tolerance epsilon for the error control. One of the following techniques is usually employed to ensure preset accuracy in an initial value problem solution while changing the step size. If the R value is within an acceptable range, then the current estimate with the RK4 is accepted. If the R value greater than epsilon, then the step size is halved because it is large, and the current estimate is recomputed with the RK4. If the R value is less than or equal to epsilon, then the current estimate is accepted, and the step size is doubled because it is small. This next procedure is similar to the previous one. The selection of the step size is a bit different. When the current step size is to be modified, the new optimal step size is determined using the delta step size adjustment factor. The procedure calculates the step size automatically, depending on the magnitude of epsilon over r. The step size is reduced if epsilon over r is less than 1 or increased if it is greater than 1. Let us consider the following first-order initial value problem. We will use the Runge-Kutta-Fehlberg RKF45 method with adaptive size control to solve the given initial value problem up to x equals 1 with a tolerance of 10 to the minus 5. And then we will obtain numerical solutions for h equals 0.1 and compare them with the given true solution. We first initialize the parameters, such as the step counter I as 0 and initial step size as 0.1. In programming, it is always a good idea to set a lower and upper bound for the interval size. Here we set Hmax as 0.5 and Hmin as 0.01. The initial value is already given in the problem statement. We will calculate the Ks first. Then we will estimate the current step value using an RK4 scheme. The convergence criterion R is calculated as the absolute difference between the RK4 and RK5 estimates. If the convergence criterion is satisfied, the current step values are assigned to X and Y. Afterwards, we can calculate the new interval size for the next step and make sure that it is not smaller than Hmin or larger than Hmax. We also need to check if X has reached the terminal point. We begin with initial value x0 equals 0, y0 equals 0, and the initial step size of 0.1. First, we compute the Ks. And then the estimate with the RK4 scheme is found to be 0.1045, 2024-46. The R value is computed as 1.6214 times 10 to the minus 7. Since this value is smaller than the tolerance value, the RK4 estimate is accepted as the first step estimate. Now we will calculate the interval size for the next step. The step size adjustment factor delta is found to be 2.353,990. The new step size is calculated as 0.235,399, which is smaller than Hmax. This means that x1 can be increased by as much as hnu. We start with the first step values, x1 equals 0.1, y1 equals 0.1045, 2245, and the new step size of 0.23, 5399, etc. We compute the Ks, and then the current step estimate with the RK4 scheme is found to be 0.375,184,792. The R value is computed as 3.9324 times 10 to the minus 6. Since this value is smaller than the tolerance value, the RK4 estimate is accepted as the second step estimate. We calculate the step size adjustment factor for the next step, which is found to be 1.06757, etc. The new interval size for the next step is calculated to be 0.249, 701, etc., which is less than the Hmax value. This means that x2 can be increased by as much as hnu. This step uses the second step values, x2 equals 0.335, 399, y1 equals 0.375, 184, etc., and the new interval size of 0.249, 701, etc. The computed Ks are listed as follows. The current step estimate using the RK4 scheme is found to be 0.676, 988, etc. The R value is computed as 2.116 times 10 to the minus 6, which is smaller than the tolerance value. Thus, the RK4 estimate can be accepted as the third estimate. Now, we determine the next interval size. To do this, we calculate the step size adjustment factor, which is found to be 1.238, 537, etc. The new step is calculated as 0.309, 264, etc. If hnu happens to be greater than hmax, hnu should be set to hmax. Or if hnu becomes smaller than hmin, then the interval size is set to hmin. However, in this case, H new is smaller than H max, and the next interval size can be chosen by as much as H new. We continue this recursive procedure in the same manner until x equals 1 is reached. The computed estimates as well as the true absolute errors are presented in the following table. The first row is the initial value, and the next 3 rows were the ones already computed. We note that the abscisses are not uniformly spaced and true errors are well under the tolerance value of 10 to the minus 5. With this note, we end this video lecture. That is all for now. See you next time with another topic. Bye.